Physics Made Easy Quota. Welcome everyone on our YouTube channel. My name is Daljit. In this video lecture, we are going to discuss about the topic optical devices. There are the different types of the optical devices. So we are going to understand some of these optical devices in this video lecture. Simple microscope, also known as a magnifying glass. This is a very common or easily available device in our day-to-day life. This is simply a convex lens of a short focal length, and we can easily observe the things by holding it near to our eye. There is a principle how this is working. Suppose we have an object AB, and when an object AB is placed between the focus and the optical center of a convex lens, a virtual, erect and magnified image is formed. Suppose that magnified image is A dash B dash, and this image formed on the same side of the lens as the object. Since a normal eye can see an object clearly at a least distance of distant vision, that is up to 25 centimeter, the position of the lens is so adjusted that the final image is formed at a distance capital D from the lens. Next, what is the magnifying power? That how much enlarged image we get by using this optical device. First of all, magnifying power is defined as the ratio of the angle subtended by the image and the object at the eye when both are at a least distance of distant vision. For a simple microscope, eye is held close to the lens. So the angle subtended at the lens may be taken as the angle subtended at the eye, and the image A dash B dash is formed at a least distance of distant vision, that is taken as D. Let the angle A dash O B dash is equal to beta from the previous diagram, and imagine that the object AB to be displaced to the new position A double dash B dash at a distance D from the lens, and let we take the angle alpha of A double dash O B dash, and then we apply the formula of the magnifying power, and the magnifying power we express in the form of the angles, and that is the beta divided by alpha. And these angles are very small, so we can apply the trigonometric functions and calculate the value of the magnifying power. We have the final expression as small m is equal to d divided by x. Now we are going to express the relation of the magnifying power in terms of the focal length. And because this is mentioned, shorter the focal length of the convex lens, greater is its magnifying power. So for this, let small f be the focal length of the lens. As the image is formed at a least distance of distant vision from the lens, so we take small v is equal to minus d by using the proper sign conventions. Then we use the lens formula, that is 1 by v minus 1 by u is equal to 1 by f. Then we put the values of the v and the u, and u is equal to x, and by using the sign convention this is equal to minus x. We get a relation in the form of the 1 by x. Then by doing the respective calculations, by taking the d as a common, we create a relation d upon x is equal to 1 plus d by f. We know that d upon x is equal to the magnification power that we did in the previous slide. So we just replace the d upon x by m, and we get a new relation, m is equal to 1 plus d upon f. So this is very much clear from this relation that shorter the focal length of the convex lens, greater is its magnifying power. There are the various uses of the simple microscope or magnifying glass. In our day-to-day life, we used to see the objects in the magnified view. The first, it is used by the watchmakers or the jewelers to have a magnified view of the small parts of the watches and to do the jewelry work in a very fine way. Also, it is used to look at the words or letters in a book in a magnified way. It is also used to magnify the texture of the fibers or the threads of the clothes. Also, it is used in magnifying the engravings and the details of stamp, and this is used in a science laboratories for reading the different scales, like for reading the scale of the vernier caliper. Compound microscope is another optical device that is used to see magnified image of tiny objects. But this device is different from our previous optical device, that is from the simple microscope. A good quality compound microscope is producing magnification of the order of 1000. How this is differ from the simple microscope? Because in this device we have the two convex lenses placed inside it. It consists of the two convex lenses of short focal length, and one is known as the objective, another one is known as the eyepiece. Objective is positioned near the object that to be magnified, and this convex lens, which is named as the objective, is of the very short focal length and having small aperture, and we give a symbol f0 to the focal length of the objective. Whereas eyepiece is another convex lens that have comparatively large focal length as compared to the objective lens and having the large aperture. It is positioned near the eye to observe the final image. The distance between the two lenses can be varied by using rack and the pinion arrangement. Now we are going to understand about the working. First of all, look at the diagram. There are the two lenses. One is known as the objective, which is near to the object, and the other one is known as the eyepiece. So the first, when the final image is formed at a least distance of distant vision, we have an object which is named at a AB. This object to be viewed at a place at a distance u0, slightly larger than the focal length f0 of the objective. The objective form a real, inverted and magnified image a dash b dash of the object AB on the other side of the lens O, that is on the other side of the objective lens, and this is also shown in the diagram. The separation between the objective and the eyepiece is so adjusted that the image A dash B dash lie within the focal length FE of the eyepiece. The image A dash B dash then act as the object for the eyepiece, which act as a simple microscope. The eyepiece form a virtual, magnified and the final image A double dash B double dash of the object AB, and this is also clearly observed in the diagram that the final image A double dash B double dash is inverted with respect to the object AB. Now about the magnifying power of a compound microscope. This is the ratio of the angles. First one, that is the angle subtended at the eye by the final virtual image, that is A double dash B double dash, to the angle subtended at the eye by the object when both are at a least distance of distant vision from the eye. So we have the formula m is equal to beta divided by alpha. Beta and alpha are the respective angles subtended at the eye by the final virtual image and by the object. As the angles are small, so we can apply the trigonometry functions tan beta divided by tan alpha. Again, by use the mathematical formula, we can put the formula by taking the respective triangles from the diagram, and we have the relation, that is m is equal to h dash over h into d upon ue. H dash over h is equal to the m naught, that is a magnifying power of the objective lens, and d upon ue is equal to the me, magnifying power of the eyepiece. Then we have the relation, that is m is equal to m naught into me. That is, here we we replace m naught by again put the value h dash over h, and for the h dash over h for the lenses is equal to v naught upon u naught. Why we put it as a v naught upon u naught? Because these distances are for the objective lens. As the eyepiece acts as a simple microscope, so we have one relation from our previous optical device, and we use that relation that is a 1 plus d upon f of the magnifying power. Just by putting the subscript e with m or with f, we make this relation for the eyepiece. Then we have the relation me is equal to 1 plus d upon fe. Then as we get the relation of the magnification power, that is m is equal to m naught me, we know the value of the m naught in terms of the object distance and the image distance, that is v naught upon u naught, put that value, and for the me we put the expression that we gained from the simple microscope. So the final expression for the magnifying power is v naught u naught, it get multiplied with 1 plus d upon fe. So we have the two relations. These relations are useful in case of the numericals, that is m can also be written as m naught me, and m can also be written in terms of the v naught upon u naught multiplied by 1 plus d upon fe. Now as the object AB is placed close to the focus f naught of the objective, so this is regarded as a special case. If such a thing occur, then we just replace the u naught with the f naught, and we know that the focal length for this case is taken as the negative by using the respective sign conventions. So we get a relation that just get in the form of the f naught by replacing the u naught, and also the image a dash b dash is formed close to the eye lens whose focal length is short. Then what we do, we just change the value of the v naught to the L, that is the length of the microscope tube or the distance between the two lenses. So we get a new formula m naught, that is earlier equal to v naught upon u naught, now get changed to L upon minus f naught. So put the value of the m naught in the expression of the magnifying power of the compound microscope, we get a new relation in the terms of the length of the microscope tube. So small m is equal to minus L divided by f naught, it is multiplied with 1 plus d upon fe. So this is for the magnifying power of the compound microscope. Now the second case, when the final image is formed at infinity by a compound microscope. This is possible only when the image a dash b dash lies at a focus of the eyepiece, that is f dash e. It is clearly observed in the given diagram. And also one more condition, that is ue is now equal to the fe. So after following these conditions, we get a final image at the infinity, and the magnification due to objective, that is m naught is equal to h dash over h, that is also further equal to L upon minus of f naught. Why we replace the word e with an o? Because this is a magnification due to objective, so we have to follow all the subscripts with the o that denotes the objective. And the angular magnification due to eyepiece is given by the expression me, that is equal to d upon fe. These expression we already understand in the previous slides. And then the total magnification by using the formula m is equal to m naught o into me. Just put the value, we get the final expression minus ld divided by FOFE. So obviously it is clear magnifying power of a compound microscope is large when both FO and FE are small, because they are very inversely with each other. Now the next optical device is the astronomical telescope. This device enables us to see distant objects clearly. It provides an angular magnification of the distant object. This device is a refracting type telescope that is used to see heavenly bodies like stars, planets, satellites, etc. So now we are going to study how this device is working. There are again the two cases. The first case, when the image is formed at the least distance of distant vision, and next of course the second case will be when the image formed is at infinity. So firstly we are going to understand the case number 1, when the final image is formed at a least distance of distant vision. So first of all, look at the diagram, and you can clearly observe that from the diagram it is clear a parallel beam of a light coming from the distant objects fall on the objective at some angle, let that be alpha. The objective focus the beam in its focal plane and form real, inverted and diminished image, that is a dash b dash. Then this image a dash b dash act as an object for the eyepiece. The distance of the eyepiece is so adjusted that the image a dash b dash lie within its focal length. Then the eyepiece magnify this image so that the final image a double dash b double dash is magnified and inverted with respect to the object, and the final image is seen by the eye at the least distance of distant vision. Now what about the magnifying power? Again the magnifying power deals with the angle subtended by the eye at the final image or at the object. So the magnifying power is the ratio of the angle subtended at the eye by the final image that is forming at a least distance of distant vision to the angle subtended by the eye by the object at infinity when seen directly. So in the diagram we make the angle alpha and the angle beta. So angle alpha is the angle a dash o b dash, and the angle beta is a double dash e b double dash. So as the object is very far off, the angle subtended by it at the eye is practically equal to the angle alpha subtended by it at the objective. Now we are doing the mathematical calculation to calculate the magnifying power. Put the value m is equal to beta upon alpha. Angles are small, so we take the help of the trigonometry functions and get a relation with the help of the diagram, that is o b dash divided by b dash e. Then we use a Cartesian sign conventions and we found that m is equal to minus fo divided by ue. Again for the eyepiece, if you observe the diagram, u is equal to minus of ue and v is equal to minus d, because the final image is forming at a least distance of distant vision. But take care of the Cartesian sign conventions and introduce the negative signs. Then we use a formula 1 by v minus 1 by u is equal to 1 by f and put the values in this formula. So firstly we put the values of the u and the v. Then we do the respective calculation and create a formula for the 1 upon ue. Then we take 1 upon fe as a common and create a new formula for the 1 upon ue. We have to calculate the answer for the magnification, and we get that magnification is equal to minus of fo over ue in our previous slide. So just put the value of the ue in terms of the fe. So we have the answer for the magnification. M is equal to minus of fo over fe multiplied by 1 plus fe divided by d. So it is clearly in the expression that the fo, or we can say f naught, has a large magnifications than fe, and the negative sign for the magnifying power indicates that final image formed is real and inverted. Now the second case, when the final image is formed at infinity. So we just do the normal adjustment as shown in the figure. When a parallel beam of light is incident on the objective, it form a real inverted diminished image A dash B dash in its focal plane. The eyepiece is then so adjusted, or we can adjust eyepiece, that the image A dash B dash exactly lie at its focus, and it is clearly shown in the given diagram. So the final image then formed at infinity by following this condition, and the final image which is forming at infinity is highly magnified and inverted with respect to the object. So now we are going to calculate the magnifying power by using the formula m is equal to beta upon alpha. So the thing, which angle is taken as beta, which angle is taken as alpha, as the object is very far off, so the angle subtended by it at the eye is practically equal to the angle alpha subtended by it at the objective. So we take alpha as the angle which is A dash O B dash, and the beta is equal to angle A dash E B dash. Then we take the help of the trigonometry functions, as the angle alpha and beta are small, and we get m is equal to O B dash divided by B dash E. Then we check from the diagram, apply the sign conventions, and we found that O B dash is equal to plus F naught and B dash E is equal to minus F E. Clearly this is having the large magnification, as F naught is very greater than F E. But in the magnification there is a negative sign. So just remember, whenever there is a negative sign, it indicates that image is real and inverted.